All right, so what we're going to do today is, if anybody has any specific questions, I don't know, how many of you had a chance to look at those practice exams, but if you have specific questions, we can start with those. Otherwise, I'll probably start picking and choosing a few and just kind of showing you how I'd work through them. We've got the formula sheet that you'll have, so I think I'd kind of try to make good use of that. Are there any questions from me before we get going, or does anyone have specific questions if they've taken a look at the practice exam that they want to go over? All right. Let me make this a little bit bigger here. Okay. So we kind of started out since the last exam doing uniform distribution stuff. You'll kind of notice that it starts to take on, well, what does the distribution of sample means look like? We've got questions related to that. We then start to get some confidence interval stuff and some hypothesis testing. So those are really the kind of main kind of topics that we're going to be looking at. Right? So hopefully some of these, just to review, I'll go over these pretty quick. Some old stuff that we haven't talked about in a while is this uniform distribution. So if we're looking at that formula sheet for the second exam, which I also want to mention, if you're on Canvas and you try to look at this, and I can't remember if I already kind of showed you guys this or it was a different section. If you go to that formula sheet, I put a PDF and a Word doc. If you try to look at the Word document, it's going to look terrible here, but if you download it, I don't know what the web browser issue is, but once you download it, it'll look fine. I don't know why it does that on Canvas in the web browser, but that's what it is. So if you download it, it should look, those lines won't be all over the place. So let's say we have an example where we're told the weighting line at the BMV is uniformly distributed. Also, we're working off of practice exam A here from 0 to 60 minutes. So you've got kind of this random variable X is uniformly distributed with a minimum of 0 and a maximum of 60, right? So what's the mean and the variance of this distribution, right? Well, this is kind of goes back to, if we have a uniform distribution and everything's equally as likely, what we're really looking at is just kind of this big rectangle, starts at 0, ends at 60. Right? So if we're thinking about where the mean of the distribution is, and this one's kind of easy because the minimum is 0, but if I'm looking for the mean of this distribution, if everything's equally as likely, we can think about it as everything's equally weighted. So if I'm just looking for the mean, I'm just looking for this middle value here. I'm really just looking at where's the middle between my minimum and my maximum. So if we look at that formula sheet, and I'll show you where to find it in a second, the equation that we have for that is just add up your minimum maximum divided by 2, or find the average of your minimum maximum. That'll kind of give you the mean there, right? So that one isn't too bad here. So we have what? 60 plus 0 over 2 should be 30. All right, so we kind of think about kind of our mean of our distribution would be 30. We're just looking for the middle value there with the uniform distribution. Right? Now for the variance, there's nothing we can really it's not quite as intuitive, or we can't really kind of see a great visual of it. But if we look at this formula sheet, we've kind of got our uniform distribution equations right here. Right? So here's our mean. So that was at our minimum and our maximum. So if you have this formula sheet, maybe prior to the exam, right? One thing, I've got it written in kind of the general form here. One thing that might help is kind of write in, maybe even right next to it, print it out and write next to it, or use the Word document and type next to it. C is your minimum here. D kind of represents our maximum. So you add your minimum to your maximum and divide by 2. To get the variance, you take the difference between your minimum and maximum, you square it and divide by 12, right? That was just, we said, kind of, if you can walk through the mathematical proof, it'll always end up being that same thing. So the variance depends on kind of the range of values you could see for this uniformly distributed variable, but it's just that range squared divided by 12, right? So there, if we're looking for the maximum, 60 minus 0, so 60 squared divided by 12, which I'll work along with you kind of here today, which would be 300. So, the only kind of, I think maybe difference you could see that I'd ask like on the exam, maybe I ask for the standard deviation, in which case, what's the only other thing you have to do here? just take the square root, right? Yeah, so those two should be hopefully like kind of like the first question on the first exam where I ask you for a mean. Hopefully, like I see everybody get these right. I mean, maybe someone forgets to, take the square root if I ask for the standard deviation, but these two should be pretty easy. We know we have a uniformly distributed variable. We know that the mean and variance for that uniform distribution, those equations are right here. You could even write that, kind of like group these. Right? So identify that these are your uniform distribution equations. Maybe write that in ahead of time before you take the exam. You kind of shouldn't be too bad. Right? All right. So the next one is, what's the probability a person waits at the BMV more than 35 minutes? So this is where probably the easiest thing to do is you've got it visually, right? So we want more than 35. If I already have my uniform distribution drawn out, and actually, just as a reminder, what was our mean? Our mean was 30. So we want 35 or more. Right away, what do I know this probability has to be less than? 0.5, right? Because the area to the left and right of my mean, the uniform is kind of, it's not normally distributed, but it still has that nice property that's symmetric around the mean, right? So the area to the right of the mean would be 0.5, so the area to the right of 35 has to be less than 0.5. So if you just kind of remember that, it can prevent us from maybe making an easy mistake, which would be like maybe looking for the area to the left of 35, right, if I have this all drawn out. So when we have an equation for the density function for this uniform distribution, but probably the easiest way to do this is, remember, you're just trying to find the area of a rectangle here. Now, what's the height of this uniform distribution? If we go back, it was 1 over the maximum minus the minimum, or kind of in general like 1 over d minus c. So here, this would be what? 1 over 60 minus 0, so 1 over 60. So if I'm looking for the area of that rectangle, I would just take the height, multiply it by the width, right? So it goes from 35 to 60. So I take the difference between those two. So really just here, what? 25 times 60. Just go over this on my head. I think it's 0.41. So 0.4166 repeated. Right. So if you draw this out and kind of remember this is just the area of a rectangle, kind of the only key there is, hopefully we can identify just, you have the numbers, you can figure out what the width is. Kind of the real key here was knowing that the height of this uniform distribution is 1 over the range, right? Or 1 over the maximum minus the minimum, okay? Questions on that? All right. So what if we want the probability someone waits between 15 and 20 minutes? Right? Well, it's really the same sort of idea, right? It's just now we're going to be looking for the probability between, was it 15 and 20, I think? Right? Now, I'm trying to kind of draw this to scale, but even if we just look at this, this is clearly going to be quite a bit less than 0.5, right? The area to the left of the mean would be 0.5. We want a much smaller range. We want like just a fraction of that. In fact, we want what? A sixth of it, right? Because our interval width is 5 or 30, so you could probably actually do this a different way. You could actually just take 0.5 and multiply it by 1/6. Now it's not always easy to see that depending on what your numbers are. So let's think about it the exact same way we did the previous one. It's still the same height. Your distribution still has that same height of 1 over 60. It's just now the width that you're looking at is only 5, right? 20 minus 15. So I think this is like 0.083. 0.083 repeated. So that, just a different kind of, another problem kind of very similar to the one before. Now, what if, might be very likely I do something like this, and I have the exam written, so when I say things like that, maybe listen. what if I wanted the probability of seeing something between 15 and 20 or between 40 and 45? Well, if I know that the area between 15 and 20 is 0.083, I don't have to do a whole lot of work. What's the area between 40 and 45? Same thing, because they both got the same height. And notice the width of those intervals are both 5, right? So I'm going to find the exact same thing. So I would just kind of add those together, right? I did my math right there. 0.166 repeated. Okay. Any questions on that? That's not a problem on the exam. So this is or on the practice exam. So that's why I'm kind of adding it kind of in here. Okay. So it's kind of revisiting some old stuff. And I think probably the best way to kind of go through today, Friday, and Mondays is really kind of starting with some old stuff, and then I'm probably going to jump back to confidence intervals and hypothesis testing. Because if you notice, well, where does that stuff start? Problem 10. So 2/3 of the exam is confidence intervals and hypothesis testing, because that's what we've done a lot of. It kind of took us a little bit of work to kind of build up to that, but we need to know some things to really be able to understand those. So let's do a problem from here. I don't want to do this one because I don't think it's as hard. So let's get some practice with this one, right? So a current survey of 30 dentists finds an average starting salary of $145,000 and a sample standard deviation of 10,000. We don't know the true population mean or variance for dentist salaries. Okay? So the first thing, let's try to construct a 90% confidence interval for what the true mean is. So we can't see the true mean. We have a sample mean of 145,000. We only have a sample standard deviation. So right away, we know what distribution we're going to have to be dealing with. Yeah, almost said it. The student T, right? Yeah. So if we only have a sample standard deviation or sample variance, we'll use that student T distribution. Maybe one way to kind of keep this straight, if you're having trouble identifying when do I use the standard normal, when do I use that student T. Anytime you have a known population standard deviation and you're dealing with a mean, or you're dealing with proportions, that's when you use that standard normal or Z table. Right? Anytime you've got a sample mean and all you have is a sample, so unknown population standard deviation. Anytime you have a sample mean and you only have a sample variance or a sample standard deviation, that's where you're going to be using that student T. I guess I need to draw these better. This could almost be confused with a. So we've got this scenario. So we're going to be using that student T distribution, right? And that's for confidence intervals and hypothesis testing. Okay. So if we go back, well, actually, I think I can remember the numbers. So hopefully, we're wanting to do a confidence interval, right? You guys get this written down, the top part at least. So what we're thinking about is we've got, 145,000 was the sample mean we found. We want to find the lower and upper bound. That 145,000 should be smack dab in the middle of our confidence interval. But how do we get that lower and upper bound? We go a certain number of standard deviations to the left and a certain number of standard deviations to the right. Now, the number of standard deviations that we go to left or right depends on kind of what level of confidence we want to say things with, right? What area do we want outside of that confidence interval? So if we just look at these values, I'm not sure, this one has a typo in it. The comma should be here, right? I'm not sure if we can really rule anything out because it looks like 145,000 is smack dab in the middle of all these confidence intervals. Now, if I'd given you an example that instead, let's say this was 146,000 to 148,000, right away you know you could rule out answer D, right? Because 145,000 wouldn't even be in that confidence interval, right? And if you're building your confidence interval around that sample mean that you found, well, it has to include that sample mean. So let's go back because I'm not actually sure what the correct answer is there, so that might be it. If we look at this formula sheet, kind of notice we've got our confidence interval equations broken down pretty nicely here, right? So here's my confidence interval for a sample mean when I know the population variance. Here's my confidence interval for a sample mean when I only have a sample variance or only have a sample standard deviation. And then here's my proportion confidence interval, right? So I'll take my sample mean, add and subtract how many standard deviations. Well, we'll find the t-value. Remember, z and t values represent the number of standard deviations away from the mean, right? And with the student t-distribution, my mean is 0, so it's a number of standard deviations away from 0 there. I'll need my degrees of freedom. So my sample size here, I believe, was 30. So my degrees of freedom is simply going to be 30 minus 1, or 29. I'll look up whatever confidence level I want, alpha over 2 on either side of it, and then multiply it by, remember, this represents my standard deviation of my sample means, but we know that that's equal to kind of the square root of the sample variance over my sample size. So let's go back to the problem. We wanted a 90% confidence interval, right? So my alpha would be, remember, alpha is just the area outside my confidence interval, but in decimal form. So at the 90% level, alpha is just 0.1, yeah. Right, 10% would be outside my interval. In decimal form, that's 0.1. Or the probability that I'm outside my interval would be 0.1. So I'm going to have alpha of 0.1, but I wanted, even the equation sheet kind of even reminds you, you want alpha over 2 on either side of the confidence interval. So when I go to my student t table, the area that I want in my tail is not 0.1, it's 0.1 divided by 2, so 0.05. I then go back here. Let me make sure I'm in the right column. Okay. My degrees of freedom was 29, so 1.699 will be that t-value that I need. So using this formula, right, I'm just going to start plugging things in. So I'll take 145,000 as my sample mean. I'll subtract to get my upper bound, subtract to get my lower bound, adding my upper bound. My t-value was what, 1.699. That's going to be the same thing below. And then we had a standard deviation of 10,000, right? So 10,000 divided by my sample size of 30. What did I not do right here? So if I look at that, if I look at that formula sheet, it's my variance that's in that numerator. I was given a standard deviation. So let me see. Oh, this will be big enough, but we can try. All right. So here, I need to have my variance, not just my standard deviation, so I have to square it, right? Essentially, all I had there was S. I didn't have S squared from the problem, so when I plug S in there, I still have to remember I have to square it, right? If I only have my standard deviation, I'm still going to have to square it. If I had my variance, right, that's the entire numerator, right? Okay? I don't know if we do this. What do we get here? 141,898, so approximately. And then I don't know what the upper bound is, but I'll kind of show you, especially kind of one way to save time on this exam. Like, if we look at those problems, none of them have like the same lower and upper bound, right? So once I find one of them, it's probably pretty safe to assume I can already identify the answer. So if I look here, kind of, and I think I rounded this, so 141,898. Well, I rounded it, right? That's pretty close, right? So once you find the lower bound, you automatically can identify what your answer is here, right? I mean, now in good practice, we could check this by also finding our upper bound, right? Plugging everything in, but instead adding it, right, to get our upper bound, right? if we do that, we should end up with kind of both these answers. But notice, like, nothing's repeated here. So once you have one of them, you can identify what the correct answer is. Okay? Any questions on that? We'll keep moving. T-tables, right? Because.
Okay, no, I was just making sure.
Yep.
When I wrote down the format, so I was like,
yeah. Yep, we use the T-table because we only had we didn't have a population variance there. Yep. Okay. All right. So with the next one, we'll keep using the same information. But there's a news article that publishes that the average dental salary is, I don't know, $150,000, right? So we're looking at dentist salaries here. So you want to test for whether or not the true average salary is less than that amount, right? So remember, whatever you want to test for, that's what your alternative hypothesis is. You'll assume the opposite is true for your null. So if I want to test for whether or not the average salary is less than $150,000, I'll assume that it's greater than or equal to that, right? So when I look down here, my null should be greater than or equal to 150,000, and my alternative hypothesis should be that it was less than 150,000, right? That's what I wanted to test for. Now you'll notice, some of these answers have the sample mean in there. That's not, you don't want to use the sample mean in your null and alternative hypothesis. I mean, I guess technically you could, right? If somehow, what you assumed to be true was exactly what you found from your sample, that seems like maybe you kind of went back and changed it after the fact. But anytime you kind of see this sample mean, it should not be showing up in your null and alternative hypothesis, right? The value in your null and alternative hypothesis comes from like some value you want to check to see, is the true population mean different than this? Is it greater than this amount? Is it less than this amount, right? And then based off your sample mean, you can kind of reject or fail to reject that is the true value, right? So we've got our null is that it's greater than or equal to 150,000, and our alternative would be that it's less than. Okay. Is that clear why that is? Is there any questions on how we identify that null alternative?
So you're saying it's a red tail test?
Well, if we have all right, so B is our answer, right?
Yeah.
What sign do we have in the alternative hypothesis? Yeah, so if it's a less than sign, you always figure out what type of tail test you have by your alternative hypothesis. So if I have a less than sign, I have a less than or a left tail test. Right? So if I have a left tail test, which of these possible answers, if I'm trying to find the critical value at the 10, 5, and 1% level, what are the only answers that even make sense here? If I'm dealing with a left tail test, yeah, only the negative ones, right? Because if I have a left tail test, and if once you identify that, you can almost just think about it like this. Okay, when I go to look up those critical values, remember, we're still looking at that student t distribution, which, even if it was the standard normal or the student t, they're both centered around 0. Once I think left tail test, the whole reason why I don't just use the term less than and greater than, like I don't even know if the book even uses the terms left tail and right tail, but it's way easier to remember, right? If I say left tail test and then I draw up my student t distribution, I think, oh yeah, I'm dealing with the left side. I automatically know when I'm looking for these cutoff values for the different levels, they're going to be to the left of 0 or negative. If I was dealing with the right tail test, it'd be positive, right? So how do I find these values? Well, I think I'll put all 3 of them up here. So here's the critical value for an alpha of 0.1, critical value for an area of 0.5, critical value for an area of 0.01. So it's essentially going to be the t-value that gives me alpha in this left tail. Right? So when I go to that student t-table, if we recall, we had a sample size of 29 earlier. So we said we were looking at degrees of freedom of, we had a sample size of 30, so we have a degrees of freedom of 29. Okay? So I go up here, what were the areas in the tail that I wanted? 0.1, 0.05, and 0.01. Right? So I go down here at degrees of freedom of 29, 1.311, 1.699, and 2.462. Right? So those are going to be my three critical values, but it'll be those values, but we said earlier, they'll be negative, right? We know that they'll be negative because we're doing the left-tailed test. So the student T table, right, is set up in such a way that it's looking at kind of that right side. So for a right-tailed test, using a student T table is a lot easier. You'll find your critical values right away. For the left-tailed test, you have to remember, well, this is a symmetric distribution, so it's going to be those same values, but for a left-tailed test, negative. So the values we found there were 1.311, 1.699, 2.462, but we know they're negative because it's a left-tailed test. Yeah. Okay.
You don't have to work anything out on that one, you just knew?
So
just because you knew, or because?
all you're doing there when you're identifying the null alternative, whatever you want to test for, so here you've got this, you know, they say it's 150,000 and you want to test for whether or not the true average salary is less than that amount. So whatever you want to test for, whatever you want to find, that's your alternative hypothesis. So we wanted to see, is it less than 150,000? So that's my alternative hypothesis. I then assume the opposite is true to stack the deck against myself, which is why we said the null is that it's greater than or equal to 150,000. Yeah, for sure. Yeah, so that's when we have a two-tailed test, right? So that was whenever we see that terminology of, so let's say here instead of less than, I said I just want to test to see if it's different than that amount. Saying is it different than 150,000 would mean is it not equal to 150,000? Yep. Any other questions kind of on these? Yeah.
So for the critical value, just to clarify,
Yep.
we find that by using the T value, and then what other value, like at the alpha, like.
Oh, so the three alphas we won here. Yeah. So we were going to get, you know, usually we could set this up, we would just test against one, but we can always test against several different alpha values. So here we wanted the 10, 5, and 1% levels, which are the kind of benchmark values, right? So at those significance levels, alpha is 0.1, 0.05, and 0.01, right? So the second thing we needed when we're doing with that student T distribution, kind of the confidence interval equation reminded us of this, but we also need our degrees of freedom. So that was just our sample size minus 1, which here our sample size was 30, so our degrees of freedom would have been 29, right? So then we went to that student T table. Here are the columns that represent the three alphas that we wanted. And then when we scroll down, degrees of freedom was 29. Is that what you were asking? Okay. So we've got our critical values. You know, this isn't a specific question, but let's say I did one where I told you to assume the test statistic. We could even kind of answer 19 before we get there. Let's assume that test statistic was negative 1.5, okay? So how would I make my rejection decisions if all I had were these critical values, okay? Well, actually, I was going to stop share here and do it. I'm going to redraw this side of the distribution to give myself a little bit more room here. So we found the three alpha values, and if I mess these up, they'll at least be close. I'm kind of doing this from memory, so I think this is what they were, right? So here was my 10% critical value, 5% significance level critical value, 1%. Right? My rejection region, right? Kind of different ways you can remember this. The kind of not great way I said is just draw arrows into the tail, and that will identify your rejection region. Another way to think about it is if I have a left-tailed test, I'd be thinking about the area to the left of my critical values. If I had a right-tailed test, the area to the right of my critical values. Two-tailed test, I had a pair of critical values, right? One on the left and right, and then kind of our rejection region there would be kind of in either tail, right? Going to the left of the negative critical value and the right of the positive critical value. So if I've got my rejection regions here from those critical values, right? Let's say I had a test statistic of negative 1.5, where would that fall? I'm just basically like a number line, right? Would be kind of right about here. So what levels can I reject that here? Well, I'm in the rejection region at the 10% level, but I'm not in the rejection region at the 5%, and I'm definitely not in the rejection region at the 1% level. So the only level I can reject at here is 10%. Okay? Any questions on that? What if I didn't have these critical values, right? So let's say, so we kind of got this down, but let's say I didn't have these critical values, and all I have is my test statistic. What other approach could I use? Not the critical value approach, but the p-value approach. Right? So what is my p-value? My p-value is the probability I saw the test statistic that I did, or sample evidence as far away from that assumed true mean as is what I found, or anything further. So for this left-tailed test, it'd be the area to the left of this test statistic, right? Now with a student t-table, it's probably easier to use the critical value approach because once we go to that student t-table, it's probably going to be that I can't find exactly negative 1.5 and I can only put bounds on my p-value. So it'll kind of remind us how we would do it if we want to use that approach. If I can get there. So same degrees of freedom. My test statistic, now once again, we're dealing with the left side of the distribution, so it kind of makes it a pain to use this student t-table because all these values are looking at the right side. But it doesn't matter, it's symmetric. So we can kind of just pretend all these are negative right now. So negative 1.5 would be in between negative 1.3 and negative 1.69. Right? So the areas to the left of these two test statistics would be 0.1 and 0.05. So the area to the left of negative 1.5 would be somewhere in between that. Right? So all I can really say here is that my p-value is somewhere in the range of 0.1 and 0.05. Okay? But notice, this actually helps me make my rejection decision pretty quickly because I only reject if my p-value is less than alpha. So for an alpha of 0.1, we'll have our kind of different alphas down here. Is my p-value going to be less than 0.1? Well, literally by putting the bounds on my p-value, I said it was less than 0.1. So that one's hopefully pretty easy, right? So kind of use the theme of kind of using every color. So here, we reject. What about at 0.05? Well, my p-value, when I put bounds on it, literally told me my p-value has to be greater than 0.5. So it's definitely not going to be less than 0.5. So I would kind of fail to reject here. Well, if it's not less than 0.5, or 0.05, sorry, it's definitely not going to be less than 0.01. So we would fail to reject there as well. Same rejection decisions as we made using the critical value approach. Like I said, it's just a little bit trickier when we're using a student t distribution to do the p-value approach because you can only put bounds on it. Now, if we're comfortable using the equations in Excel, kind of in the examples that we worked through with hypothesis testing, we could use the t.dist function, put in negative 1.5, tell it the degrees of freedom, it would give us the area to the left, and then we would kind of have the exact p-value. Right, so if we did that, once again, you can use the Excel in the exam if you want. And I would suggest only doing it if you're really confident in your understanding of whatever functions you're using. But just go real big here. T.dist, negative 1.5. Our degrees of freedom was 29. This cumulative is always 1, and then it's going to, in Excel, tell us the area to the left. That's just how all the functions work in Excel, right? T.dist, norm.s.dist. So we get 0.07 as our p-value, which sure as can be, right, would be in that range, right? And then, then it'd be easy. If I have 0.07, is that less than 0.1? Yes. Is it less than 0.05? No. Is it less than 0.01? No. Okay? Any questions on anything related to that problem? I'm guessing we answered probably answered a couple questions that were on there. Kind of jumped ahead a little bit, just kind of complete that, right? I was talking about kind of that rejection decision, We found our critical values. What's the test statistic? Well, here I gave you an assumed true test statistic for 19 because if you calculate 18 wrong, you're for sure not going to get 19 right? You're working with the wrong test statistic. So a lot more so than the first exam, a lot of these problems are going to have kind of like ask you a question, right? And then assume the test statistic was this, right? Or assume the p-value you found was this. What is the rejection decision? Right? I'll give you a lot. Like, even though they're all kind of using the same starting information, make sure you kind of read the questions to see, did I give you, kind of this assumed true value that you're now working with, so everybody's kind of starting at the same place, right? But yeah, I think that covered everything except for the test statistic, right? So in order to find that test statistic, what we're really doing was saying, okay, look, I had started out with my null alternative hypothesis was that the true amount was 150,000, which if that assumption was in fact true, my sample means, sorry, not T, my sample mean should be normally distributed around that. I found a sample mean of 145,000. So what I was trying to do is turn this into a test statistic because I want to find the p-value or plot that test statistic against my critical values. Well, those are coming from the student t distribution, right? Because I don't have a table for every single normal distribution. I only have a table for the standard normal distribution and for student t distributions. So I know that this student t distribution is set around 0. If I found sample evidence that's below what I assume to be true, right away I know my test statistic has to be negative, yeah, not less than 0.5, right?
Negative.
The p-value has to be less than 0.5 because once I turn this into a test statistic, yeah, my p-value should be less than 0.5. So I know that my test statistic will be negative, right? If I found sample evidence above the mean, I know my test statistic will be positive, okay? So if I go to my formula sheet, so first of all, if I look at these, I know A or B has to be the right answer right away. So if you remember kind of these small things, if you draw this out so that you can see, oh yeah, I found something to the left of the mean, I know my test statistic will have to be negative, it kind of prevents you from like making a really easy mistake on these multiple choice ones, right? So there will be kind of a short answer question that has quite a few several parts at the end, similar to the first exam. But in these multiple choice ones, at least it kind of lets you rule out, I mean, here I've got a 50-50 shot. And if you're guessing, why do you probably not guess B here? If we think at all about what we're doing with this hypothesis test, what would be a test statistic of negative 273 actually mean? So what that would mean is that I found sample evidence. Remember, Z and T values still represent the number of standard deviations away from the assumed true mean now. So it would mean that the sample evidence I found was 273 standard deviations below what I assumed to be true. I mean, I don't know exactly, we calculate what the standard deviation is here, but I mean, it'd have to be, pretty small in order for me to be 273 standard deviations away, right? Now, it could happen if I had a huge sample size, but I only had 30 here, right? So if I'm guessing, like, A is probably a pretty safe guess. Now, the actual equation that we use to get that test statistic, if you want to, in case I didn't give you kind of some more ludicrous possible answers, we go to that formula sheet. Oh, maybe. There we go. Here's my 3 test statistic equations. Sample mean when I know the population variance, sample mean when I only have a sample variance, and then proportions, right? So I'll be using this guy right here, and then it's just a matter of plugging my numbers in. My sample mean was 145,000. Assumed true mean was 150,000. Variance was, what were we given as the variance? Was this one we were only given the standard deviation, right? Maybe that's what it was. Yeah, so we're only given the standard deviation of 10,000. So similar to the confidence interval, when I go to plug that in, I'll need to make sure that when I plug 10,000 here, I square it, right? Because I only have the standard deviation. I want to make sure I get the variance in here. And then divide it by that sample size of 30. So another common mistake I saw in grading the Excels, just from some questions I've gotten from people via email, when you're calculating this test statistic, you don't divide by the degrees of freedom. The degrees of freedom is only used when you're looking up critical values, or you're kind of looking up p-values, or you're looking up the, the t-value to use for a confidence interval. When you're actually calculating that test statistic, right, or in the confidence interval, when you're figuring out what that standard deviation of your sample means is, this is n. This is not your degrees of freedom. This is your sample size. So you would still be plugging 30 in here when you're calculating the test statistic. Just when you're looking for like the area to the left or the right, or when you're trying to think about that distribution and areas in that distribution, do you use that degrees of freedom, right? And the actual formulas, the equations for confidence intervals and for your test statistic, you still are plugging in that sample size, okay? So we plug all our values in here, we'll end up getting negative 2.74. I'm not going to kind of just write all that out. I mean, hopefully, once you identify that formula, plugging those values in and kind of getting entered into your calculator, that should be not too bad, right? That should be the kind of easier part of it. It's kind of identifying which formula do I use, what type of example do I have. That's probably a little bit more of the trickier part, right? That's probably I'm spending a little more time on some of that. So we got that test statistic of negative 2.74. Okay. Now, just for the sake of what we're doing here, I don't know. Let's say that one of the other option was negative 1.64 here, right? When I give you an assumed true value in the next problem, don't read into that at all, right? Just because it's closer to negative 1.64, if I was like, oh, well, then I must have made a mistake. It's probably negative 1.64 if you gave me the assumed true value of negative 1.5. No, I'm choosing this number for a myriad of different reasons other than that it was close to what the correct answer is. So just because the test statistic, that I give you that's assumed for the next problem, don't read into that at all, right? Probably shouldn't even tell you that, but don't read into it at all, right? It has nothing, it's nothing to do with what the correct answer actually is, okay? Okay, any questions on that? All right, so let's do 20 here, and I think we'll end on that because it's kind of related to the same problem. So let's say instead of 30, you took a sample size of 60. Which of the following is going to be true? So this is kind of something that I was trying to really hammer last class, but if we've got this test statistic equation, it looks like this, and I just went from a sample size of 30 to 60, my sample size went up, right? So if my sample size goes up, what happens to kind of this guy right here? Or what's in my denominator? My sample size goes up, this goes down, which means my entire test statistic would actually be higher. Just kind of the mathematics of it. Well, if I also remember, what did my denominator represent? It was the standard deviation of my sample means. So once I go from 30 to 60, if I have a smaller, right, my kind of denominator here, which represented a standard deviation, is getting smaller. I have a lower standard deviation or a lower variance. I'm going to get a more peaked distribution, which now means from that same sample evidence, my p-value, right, is going to be a much smaller value. Right? And kind of thinking about this differently, if my test statistic is going up, and when I say it's going up, it's really increasing in absolute value. If it's negative, it's becoming a greater negative value. So my test statistic, I guess I can kind of leave the old one up where our old test statistic would have been. Our new test statistic is going to be somewhere over here, which means, right, my p-value, or the area to the left, is going to be smaller. Right? So when I have a higher sample size, I get a higher test statistic, kind of greater in absolute value, a smaller p-value, right? I think about it as my p-value is going down here, which if my p-value is getting smaller, am I more or less likely to reject the null? Well, if I only reject when the p-value is less than alpha, if my p-value is getting smaller, it's going to be more likely that that's less than alpha, right? So those are going to be all the things that are kind of true from taking that higher sample size. So when we look at those answers, we're looking for any of those things, right? Greater test statistic, lower p-value, or more likely to reject the null, right? So if I look at these possible answers. The new test statistic will be smaller. And here, I'll probably actually change the language. I would have the phrase in absolute value, right? So we're thinking about if it's negative, smaller would mean that it's like getting closer to 0. In fact, even though it actually would be greater, right? Because we're dealing with negative values. So that's not true. We just said that it's going to be larger in absolute value. The p-value would be larger. We said that's not true. The p-value is going to be smaller. But we did say we would be more likely to reject the null. So here the answer would be C. Okay? Any questions on that? Okay with that? Okay. So I think that's probably all we'll do today. We've got several other problems we can do from practice exam A, more from practice exam B. Oops. So we'll start working through those next class. If you have specific problems, like I said, we can start with those. I have the exam pretty much written. So it's going to look similar to the last one where it's about 20 multiple choice problems. And then a short answer portion at the end that has like 4 or 5 questions associated with it. There might be a bonus question. It might be. I can neither confirm nor deny. So similar kind of deal as the last exam. You'll upload something for that short answer question, whether or not it's your work in Word, Excel, handwritten, kind of upload a photo of it. Any other questions for me? Like I said, we got a little bit of time before it, so if you start having questions the next couple classes about it, feel free to kind of ask them. We'll just keep doing some more review and hopefully, get you guys to do well on that. Really bolster up your kind of grade and not have to worry so much about the final if you do well in those other exams. So I will see you guys on Friday, right? Today's Wednesday.